Ever stop to think about the absolute unbreakable speed limit of the universe? For over a century, we've been taught that nothing can travel faster than the speed of light. It's the law, the ultimate rule of the cosmic road. But what if I told you that rule has a bizarre, mind-bending loophole? Imagine two particles born from the same event, sharing an invisible, instantaneous link. One particle could be on Earth, and its twin could be on the other side of the galaxy. The moment you measure one, its twin, light years away, instantly knows and changes its state. This isn't science fiction. This is quantum entanglement, a phenomenon so strange that even Albert Einstein called it spooky action at a distance. Today, we're diving deep into the paradox that could redefine reality itself. We'll explore why this isn't just a quirky scientific fact, but a potential key to technologies that sound impossible, and a challenge to everything we think we know about space, time, and speed. Get ready, because the universe is about to get a whole lot weirder. Let's start with the basics. The classical world we live in is predictable. Throw a baseball, you know where it's going and how fast. But in the quantum realm, that certainty vanishes. Here's the core myth, that particles have a fixed state before you look at them. We tend to think a coin is either heads or tails before it lands. But in the quantum world, before you measure it, a particle's properties like its spin exist in a state of superposition. It's both up and down at the same time. This is where entanglement gets truly wild. When two particles become entangled, they become a single interconnected system. Imagine two gloves in a box. You take one to New York and leave the other in Los Angeles. The moment you look at the glove in New York and see it's a right-hand glove, you instantly know the one in LA is a left-hand glove. Quantum entanglement is like that, but way more profound. The particles don't just remember their twin state. Their destinies are literally linked. The fascinating truth is that this connection is not a matter of a predetermined outcome. It's an active, instantaneous correlation. When you measure the spin of particle A to be up, the spin of particle B, no matter the distance, collapses to down at that very instant. There's no signal traveling between them. No information is being sent. It just happens. The ultimate reality is this spooky action challenges our most fundamental assumptions about cause and effect and locality, the idea that a particle can only be influenced by its immediate surroundings. This isn't just about speed. It's about a hidden, interconnected fabric of the universe that we're just beginning to glimpse. It makes you wonder, what other secret connections are out there just waiting to be discovered? This is the part that even the great Albert Einstein couldn't stomach. He, along with Boris Podolsky and Nathan Rosen, proposed a thought experiment in 1935, now known as the EPR paradox, to argue against the completeness of quantum mechanics. The myth was that this spooky action at a distance must be a flaw, a sign that there were hidden variables, undiscovered properties or instructions, that the particles secretly carried from the moment they were entangled. Einstein believed this would preserve the principle of locality, the idea that nothing can influence something else faster than light. The reality, however, proved Einstein wrong. In the 1960s, physicist John Bell formulated a theorem, Bell's theorem, that provided a way to test this. And then in the 1980s and more recently, experiments by Alain Aspect and others definitively proved that Bell's inequality was violated. This is a monumental fact. It showed that there are no hidden variables. The correlation is truly non-local and instantaneous. The two particles are not simply following a pre-written script. Their fates are genuinely intertwined in a way that defies classical physics. This means that a measurement on one particle does have an instantaneous effect on the other, regardless of distance. It's a connection that exists outside our normal perception of space and time. So while you can't use it to send a message faster than light, it proves that the universe operates in a way that is profoundly interconnected and far more mysterious than we ever imagined. Think about that for a second. A concept so radical it forced the greatest mind of the 20th century to rethink his own theories. So, if this connection is instantaneous, why can't we use it to build a super-fast communicator? This is a common myth that Hollywood loves to exploit. The reality is that the no-communication theorem is a fundamental law of physics. The spooky action is a correlation, not a form of information transfer. Let me explain. When you measure particle A and its spin collapses, particle B's spin collapses simultaneously. But here's the kicker. You don't know what state particle A will collapse into before you measure it. It's random. It could be up or down with equal probability. So the person on the other end, with particle B, just sees their particle randomly collapsing. They have no way of knowing whether their particle collapsed because of your measurement or just because of its own random quantum nature. To receive a message, you need to be able to control the information being sent, and you simply can't do that with entanglement. The information you're trying to send, the message, is encoded in the sequence of measurements, and that sequence is fundamentally random and unpredictable from the get-go. This is a crucial, often overlooked fact. Entanglement is about a shared instantaneous reality, not about a controllable communication channel. It's a bit like two people flipping two coins that are secretly linked. When one person gets heads, the other gets tails. They know their coins are linked, but they can't make the coin land on a specific side to send a message like, "I got heads." The connection is real, but it's not a highway for data. It's a testament to the fact that, while the universe is weird, it's also incredibly clever about protecting its speed limits. While we can't use entanglement for a Star Trek-style communicator, its paradoxical nature is the engine behind what could be the next technological revolution: quantum computing. The myth is that quantum computers are just faster versions of our current computers. That's a massive oversimplification. The reality is that they work on an entirely different principle. Instead of using bits that are either 0 or 1, quantum computers use qubits, which, thanks to superposition and entanglement, can be 0, 1, or both at the same time. A key fact here is that as you entangle more and more qubits, their combined computational power grows exponentially. While a classical computer would have to check every possible solution one by one, a quantum computer can perform a massive number of calculations simultaneously by exploring all possible states at once. This is the power of entanglement. It allows for a state of shared knowledge between the qubits that supercharges their processing ability. A single quantum computer could tackle problems that would take a classical supercomputer billions of years to solve, like developing new medicines, creating unbreakable encryption, or optimizing global logistics. The connection is that this bizarre, spooky action at a distance is not just an abstract idea. It's the fundamental building block for a future where we can solve problems that are currently beyond our grasp. It's a perfect example of how the weirdest parts of science often hold the greatest potential. Let's talk about secrets and how entanglement could make them truly unbreakable. The myth about current encryption is that it's flawless. In reality, it's just very, very hard to break. A powerful enough computer, given enough time, could eventually crack any code we have today. Quantum entanglement, however, offers a solution that is mathematically and physically impossible to break. Here's how it works. Two people, Alice and Bob, entangle two photons. They send one photon to Bob while Alice keeps the other. They use the unique random properties of these entangled photons to create a shared secret key. The truly amazing fact is that if a third party, Eve, tries to intercept the photon to read the key, her action of measurement will instantly break the delicate entanglement. Alice and Bob will immediately know their key has been compromised because their entangled particles are no longer behaving as they should. The connection here is that entanglement sensitivity, that spooky action we talked about, becomes a form of ultimate protection. The slightest peek from an outsider instantly alerts you to the security breach. This isn't just a harder way to create a key. It's a way to create a key that can't be read without leaving an obvious, unmissable trace. It leverages the weirdness of quantum mechanics to create a system that is literally impossible to eavesdrop on, making it the future of cybersecurity. Makes you wonder what other seemingly useless quantum traits could be harnessed for our benefit. Now for a term that really sounds like science fiction: quantum teleportation. The myth here is that we're talking about teleporting people, like in Star Trek. The reality is far more subtle and in many ways more profound. Quantum teleportation doesn't move matter, it moves information. Specifically, it transfers the quantum state of a particle from one location to another, without the original particle traveling through the space in between. It uses entanglement as a bridge. An astonishing fact is that in 2019, scientists successfully quantum teleported information over 27 miles of optical fiber. The connection to entanglement is that it's the entangled pair of particles that creates the bridge needed for this transfer. By performing a joint measurement on the particle to be teleported and one half of the entangled pair, the quantum state of the original particle instantly imprints onto its entangled partner at the distant location. This is not about sending a signal. It's about a non-local transfer of information. It could one day be the foundation for a quantum internet, where quantum states, the very currency of quantum computers, can be transmitted across vast distances. This technology has the potential to connect quantum computers globally, creating a network with unimaginable processing power and security. We're not beaming up Scotty anytime soon, but we're starting to understand how to move the fundamental building blocks of information instantaneously. This paradoxical reality has mind-boggling implications for our very understanding of the universe. The myth is that our universe is a series of independent, separate points in space and moments in time. Entanglement challenges this by suggesting a deeper interconnected reality. The reality is that the spooky action implies a kind of non-local connection that goes beyond our three spatial dimensions and the one dimension of time. A key fact is that some physicists believe entanglement hints at a deeper structure, where space and time themselves emerge from this web of quantum connections. The very geometry of the universe, what we call space-time, might not be fundamental. Instead, it could be a consequence of the underlying quantum entangled relationships between particles. This is a revolutionary thought. It suggests that if you could somehow untangle the universe, space would cease to exist. The connection here is that what started as a weird quirk in physics, the entanglement paradox, could be the key to a unified theory of everything, linking the quantum world with the massive scale of gravity and space-time. It completely inverts our traditional view of the universe. What if distance is just an illusion of our perspective, and on a deeper level everything is connected? Finally, let's bring this back to our daily lives, or at least the technology that will soon impact them. While we wait for quantum computers and the quantum internet, entanglement is already being harnessed for an incredible application: ultra-sensitive quantum sensors. The myth is that this stuff is only for labs. The reality is that entanglement can be used to make devices that are far more precise than anything we have today. A key fact is that an entangled pair of particles can sense tiny changes in their environment with a precision that would be impossible for a single, non-entangled particle. For example, entangled photons can be used to create sensors that can detect minute magnetic fields, allowing for earlier and more accurate medical diagnoses, or to create next-generation gyroscopes for navigation systems that are so precise they could guide a spacecraft to the other side of the solar system with incredible accuracy. The connection is that this spooky sensitivity, which seems so odd and useless on a macro scale, is precisely what makes these sensors so powerful. They're leveraging the fundamental weirdness of entanglement to create practical, real-world tools that will change medicine, defense, and exploration. The paradox of instantaneous connection isn't just a philosophical puzzle. It's a blueprint for a technological future we're just beginning to build. What a ride, right? Quantum entanglement is one of those topics that proves reality is stranger than fiction. If you've been as mind-blown as we have, hit that subscribe button and ring the notification bell so you don't miss our next deep dive into the unknown. And tell us in the comments, which fact about quantum entanglement did you find the most bizarre or fascinating? So we've gone from a simple paradox to a potential revolution. We've seen how the spooky action at a distance that challenged Einstein is now the foundation for quantum computing, unbreakable cryptography, and ultra-precise sensors. We've learned that while it doesn't allow for faster-than-light communication, it reveals a deeper, non-local connection that could redefine our understanding of space and time. The quantum entanglement paradox isn't just a scientific curiosity. It's a window into a universe far more mysterious and interconnected than we ever thought possible. As you go about your day, remember that on a fundamental level, everything is linked. What other paradoxes are out there, waiting for us to unravel their secrets?